In this video, we're looking at the method of substitution. So this method is generally used for products and quotients where one of the functions is a derivative of the other function. So we need to look at the parts of this and try and think how that goes together. We use our substitution to rewrite the question so that it simplifies to one of the standard integrals. So if we have a look at this example here, remember before we would have used here, if we had y is equal to the square root of x cubed plus 5, we would have called this our u. So u is equal to x cubed plus 5. And then y is equal to the square root of u, or u to the power of a half. We're using that same concept now to keep going through. So here, we're going to say u is equal to x cubed plus 5. If we differentiate this with respect to x here, we get 3x squared here. And that's what this is here. So this matches our 3x squared here. So this is our du on dx. And then here we've got the square root of our u. So here our integral over here becomes our integral. Here we've got du on dx, and then we've got u to the power of a half here, dx. So here we can integrate our u to the power of a half. So here, our u to the power of a half becomes a half plus 1, or 3 on 2, and here divided by 3 on 2. And remember, when we're actually differentiating, we end up multiplying by this du on dx here, and that's what we need to divide by as well. So if we had our du on dx, and we're dividing by this du on dx from our u here, and this 3 on 2 from our power here. So these cancel out. So what this becomes, here we get our integral. We've got 3x squared. Here we've got u to the power of a half dx here, so this becomes here. So here we've got 3x squared. We've got here our u to the power of a half, or u to the power of 3 on 2 on 3 on 2, and we've got our du on dx, and we substitute our u and our du on dx back in. So here we're going to be getting 3x squared multiplied by x cubed plus 5 to the power of 3 on 2, divided by 3x squared. Our 2 is going to move up here, so here we're going to multiply by 2, and here by 3. Our 3x squares cancel out. We end up with 2 x cubed plus 5 to the power of 3 on 2, all divided by 3. Plus our constant c there. So we're just using this substitution, and we've got to go backwards. So here we would have worked this one out. Here we've got our u is that, and so here our du on dx here is our 3x squared, and our y is equal to u to a half. Dy on du became a half u to the negative a half. When we put them together, we multiplied this one by this one. So working backwards with our integrating, we need to divide by this du on dx here. So we've got another example here. We want to evaluate the integral of here, our cosine of x squared multiplied by sine of x dx. So here, this becomes our u. So u is equal to cosine of x. Du on dx therefore becomes negative sine of x. And so see how this almost matches. To get our negative sine of x, we're going to have to put a negative in there and a negative out the front. So now we're matching this du on dx. We put a negative out the front. And so now that's our du on dx, and here we've got u squared. So here, when we go through this, our cosine of x, here we're to the power of 2. We're going to make this to the power of 3 and divide by 3. And here we've got our du on dx times our negative sine of x, and here we had times our negative sine of x, and we have our negative sign out the front here from this part. So we end up here with negative cosine of x cubed. Our sine of x's and those negatives cancel out there, on 3, plus our constant c. So if we move on to this next question here, we've got x times sine of x squared. And so this x squared here is going to become our u. U is equal to x squared. Du on dx is therefore 2x. Here we have x. So what we can do, we make this the 2x that we need to be our du on dx, and we're going to times it by a half out the front. So here we end up with, we've got our integral, a half times our integral, we've got 2x multiplied by sine of our u, which is x squared, dx there. So we keep going here, we've got a half, here we've got our 2x, here that comes out when we go through here. We're going to end up with our sine of x integrates to negative cosine of x squared plus our constant c. So we don't need to write that step in every time. If we've got our du on dx here at the front and then our function of u here, then we don't even have to write that step in when we're getting rid of that there. So keeping on going with these questions here, we're saying here, well, this is our common function, square root of x. U is equal to the square root of x, which is equal to x to the power of a half. Du on dx, therefore, becomes here a half x to the power of negative a half, becomes 1 on 2 root x. When we think about this here, this is the same as here, 1 on the square root of x multiplied by cosine of the square root of x dx. So here we've got 1 on the square root of x. We want to make this 1 on 2. So that's a half, and we're going to multiply it by 2 out the front here. So now we're going to work through with this. We've got here our du on dx. We've got our 2 out the front, our du on dx here. Now we just integrate our cosine here. So this becomes sine of the square root of x plus our constant c. So if we move on to this next one here, we've got here natural logarithm of x. So here we're saying, well, u is equal to our natural logarithm of x. So here when we differentiate this, du on dx, remembering our natural logarithm becomes 1 on x. Here our integral is the same as 1 on x multiplied by natural logarithm of x dx here. So this is our du on dx, and then this one here is our u. So what we've got, du on dx multiplied by u here. So when we actually go through and we integrate this, we're going to end up here with our natural logarithm of x, power of 2, divided by 2, plus our constant c. So our substitution works because we're using our function of a function rule here. So here, when we worked through, we had here our function of g of x multiplied by here a differential of g of x, where u is our g of x, so our du on dx is our differential here of g of x. So du is equal to our differential g of x dx. We just need to remember we need to get our function. When we're integrating here, we need our du on dx and then our function of u here, dx. And we end up with our answer there. So if we do another example from the notes here, we want to differentiate here 2x plus 3 to the power of 7. If we were to differentiate this, so here d on dx, remembering Here, well, u is equal to 2x plus 3. du on dx is equal to 2. So here our y is equal u to the power of 7. dy on du is equal to 7u to the power of 6, is 7 times 2x plus 3 to the power of 6. So now when we work out here our dy on our dx, will be our du on our dx multiplied by dy on du, which is here 2 multiplied by here our dy on du, 7 times 2x plus 3 to the power of 6. So we end up with 14 multiplied by 2x plus 3 to the power of 6. So now we want to find the integral of 2x plus 3 to the power of 6 here. So here we go, okay, well this is our integral here where our u is equal to 2x plus 3. Our du on dx here is equal to 2. So we need to have our du on dx out the front here. So we have the same setup here. So our integral of 2x plus 3 to the power of 6, we need this du on dx here to be 2. To make this still the same, we've multiplied it by 2. So out the front of our integral, we're going to multiply it by a half. So it ends up being 1 times that here. So now when we go through, we've got a half times here. When we multiply this through, we've got here 2x plus 3 to the power of 7 on 7. And here our 2, our du on dx disappears out, plus our constant c. So we're going to end up with here 2x plus 3 to the power of 7 on 14, plus our constant c.